I am audible there, and the screen is visible at your end. Am I audible properly? Okay, the presentation is also visible there. Okay, so today we will be discussing. Now, I hope you should have, understood the K maps and their simplification properly. In case some of you, or any one of you has any question regarding simplification of K maps, you can ask me so that I can help you, because many things now will be followed on the basis of K maps. Is there any doubt from K maps? Do anyone have any confusion or any question from K maps or simplification from K maps? Okay. Many of you are saying no, then fine. Now, if there is no confusion, that's really good. Then we will be now talking about a few examples of practical circuits. As of now, we were taking only the some given truth table, and then we were trying to write down K-map for it and then further simplify. Okay. Now we will be seeing some circuits of practical importance and then try to see that how K-maps can help designing those circuits. One, set of circuits which we will be considering is arithmetic circuits. I mean, the circuits which are used for doing arithmetic operations of binary numbers. Moreover, I would like to say that I won't be discussing now the detailed design of the circuits, but briefly showing you up the truth table for those circuits, which maybe you would have done earlier as well. And then once you know the truth table, then you can actually understand how to design that particular circuit in its simplest form. One such circuit is called half adder. So half adder means a circuit add any two binary numbers. So this is a truth table or example for that. If we have two binary numbers, suppose A and B, and we have to add them, then there will be two outputs actually. One is sum bit, which we call S, other is carry bit. I mean, if you add any two binary numbers, there will be a sum, and there may or may not be a carry depending upon what the bits are. So suppose you add 0 to 0, sum should be 0, carry should be 0. If you add 0 to 1, sum should be 1, carry 0. If A is 1, B is 0, sum is 1, carry is 0. And if A and B both are 1, sum is 0, and there will be 1 carry, right? So now, given this truth table, I'm sure you will be in a position to design a circuit for this. The first part, that is sum part, is, so we have to write down two independent truth table K maps. One K map for S as an output and AB as inputs. Second map for C as an output, AB as inputs. So two K maps, simplify the K maps, then connect the inputs accordingly, and that's it, you are done. So this part is something like an exclusive OR gate, isn't it? But when you write down K map for this, then you will be able to identify that indeed the simplified expression is nothing but the expression for exclusive OR gate. Can you try to simplify this? Let us try to simplify this. This is very simple. Two variable K map. You write down two variable K map and then simplify that for S and write down the Boolean expression from that K map for S in terms of AB. Okay, let us try it. You do it, then let me know if you can do that really. Write that small K map. It is going to be very, very simple, two variable K map, but it's a quick practice to you. And then finally, try to look for pairs. There won't be quads here, I think. Uh, Two variable map. Yeah, there can be, but that would be very rare. I mean, in two variable. So, Jyoti, I hope you didn't write down the expression for exclusive OR gate directly, and you indeed actually solved the K map. Because we know we have studied what is the expression for exclusive OR gate. That is fine. But how to obtain this using K maps is the main thing which we have to do here. Well, that's quite simple. Similarly, you can write down expression for carry. Then there is something called full adder. So why it is called half adder, this earlier one, is because there are only two inputs. Okay. So means this kind of adder can add only two binary numbers. Then you will ask, okay, then usually we have to add two binary numbers. But then it doesn't take that carry from the previous uh, previous set of bits. Suppose you have a multi-bit addition. Suppose you want to do 4-bit addition, right? So the least significant bits can be added with the help of half adder. But when you go to the next set of bits, we have to keep a provision for carry as an input, which must be coming from the previous bits, that is LSB, or lower significant bits, you can say, because a full adder should have three input options: input of first number or the value of second number, and carry, which may be coming from the previous bit. That is what we call the full adder. So similarly, this will be the truth table for a full adder. You can actually see this. It's a very simple binary addition only. But here is the truth table for that full adder. And then again, you can write down the K map for Sn in terms of ABC. So now the K map is going to be a three variable K map. Rather, we will have two K maps of three variable each, one for some bit, nth, n means here the location of the bit in the binary number. So for a 4-bit case, you may write down n equal to 0 for least significant bit, n is equal to 1 for next one, and n is equal to 3 for most significant bit. So similarly, there will be two truth tables, two K maps, and then you can solve them and then write down expression for Sn, and then obtain what will be the full adder circuit. We will be discussing half adder and full adder in coming classes, but by then I give it as an homework to you that you solve these truth tables with the help of K maps. There I won't be doing it in detail. I will be directly showing the circuit. But yes, you should be in a position to get that yourself independently. Is this clear till now? Is everything okay? Okay. Next thing, we may come across operation of subtraction with the help of digital or binary circuits. So binary subtractor, similarly, I mean, there is a half subtractor, 0, 0. If you subtract 0 from 0, output is going to be 0. There is no carry. Carry, rather than carry, we should say borrow, B, or you can say C for borrow bit, because B is already resolved here. So that's why they have written C here. It's not carry. I mean, borrow taken from the higher significant bit. Then if you subtract 0 from 1, output will be 1. If you subtract 1 from 0, output will be 1, and we have to borrow 1. I mean, carry this has to be 1, and so on. I mean, that's how you can write down the truth table and then can design the circuit for this. Another example is of a full subtractor. Then again, truth table or see the various options for the truth table, and then you can obtain the corresponding circuit with the help of K maps. I will upload a PDF, I mean, some pages of that PDF. These circuits have been solved and discussed in detail in the book by R.P. Jain. I don't know if you have bought it or not, but I recommend you must buy that book. That's a very good book for digital electronics. But I will also upload these relevant pages of that book for your reference so that you can study the details of solving K-maps and implementing the circuits from that book. Okay, these are solved there in very detail, but I would recommend that you first do it yourself, then try to see solutions given there. Other very important circuit in digital electronics is BCD to 7-segment decoder. Have anyone of you heard of this BCD to 7-segment decoder? Or have you seen those 7-segment displays or 7-segment decoders? Have you seen them? Anyone? Oh, I'm sure you all have seen them, but you probably didn't know that these are 7-segment displays or decoders. You would have seen this kind of digital displays somewhere at some stage in your life, I'm sure. Isn't it? Where your old school, those digital watches were actually employing this kind of displays. And then at many other places, even in our lab, I think many instruments are based upon these kind of digital displays. They display numbers with the help of these 7-segment displays. So these are called 7-segment displays. Why they are called 7-segment display? Can anyone guess? Why they are called 7-segment display? Yes, anyone? They are called okay. They are called 7-segment display because they can display, first thing, binary coded decimal BCD to 7-segment decoder. So you may have a decimal number written in binary form. Suppose BCD, I don't know whether we discussed binary coded decimal code or not. So in BCD code, you reserve 4 bits. You reserve 4 bits for representing binary number in usual way, right? Like, okay, 0000 is 0, 0001 is 1. Similarly, 0011 is 0011 is what? 3, and so on. And then you represent all the numbers up to 9. Then for 10, we don't, we don't use the combinations of that 4-bit system for higher values. We only go up to 9. That coding is called binary coded decimals. Okay. Now, how should the binary coded, these are, how to display any binary coded decimal number in a 7-segment display? So a 7-segment display has 7 LEDs. Let us try to see that as LED made up of this suppose is made up of 7 type of LEDs, and these are suppose linear LEDs, linear shaped LED. Then you have one LED here, second, third, fourth, fifth, sixth, and 7th. And interestingly, based upon which of the 7 LEDs glow or are glowing, we have these numbers here. For example, if you have to display 0, A, B, C, D, E, F, all should glow. That would give you 0, right? For 1, what we should be getting as on LEDs, B and C. Only B and C should be switched on. That will give us 1. For 2, what should happen? A, B, G, E, and D should be on. Right. For 3, A, B, C, D, and G should be on. For 4, F, B, G, C should be on. F, B, G, C should be on. That will display 4, and so on. So that is what is called a 7-segment display, and these were very popular displays and were used to represent decimal numbers uh, in this form. Okay. Now question here is that how we can design a circuit that can actually convert that binary coded decimal into these 7 segment displays. So the output of that circuit should be that, okay, when you have 0000 as input, so it should have 4 inputs and 7 outputs rather, right? So if you have 0000 as inputs, what should be the outputs? Outputs at A, B, C, D, E, F should be 1, whereas G should be 0. Similarly, if you have 0001 as input, the output at B and C should be 1, all others should be 0. That's something great or interesting. So that is what is the truth table for this BCD to 7 segment decoder, 7 segment display decoder. You can see here, right? When you have to display decimal 0, the corresponding binary code is 0000. All A, B, C, D, E, F should be 1 and G should be 0. For 1, here you can see B and C should be 1, others should be 0. For 2, you can now check C, you can see this C, you have to write down 2. Okay, this way. Oh, for 2, what is he saying? Okay, this is not that C. Okay, sorry. This is your binary decimal. Sorry, this is binary code for 2. And what all should be on? A should be 1, B should be 1, uh, A, B, G, E, D. You can check here. A, B, D, E, and G should be 1. That's what is representing the truth table for a BCD to 7 segment display. Now is the task, which is really interesting. Is this clear up to this point? What we are doing in BCD to 7 segment display? Is everything clear till now? Okay, fine. So let us discuss this. This is very interesting circuit. So I would like to discuss this in little detail. Um, so these are the K maps for each of A, B, C. Now you can, okay, I would recommend you to either note this table in your notebook or take a screenshot if so that a screenshot won't work because you are online, your screen is busy as long as lecture is going on. So you quickly note down this truth table for this 7 segment decoder in your notebook so that you can understand these K maps. Okay, giving you maybe like 2-3 minutes. I'm giving you 3 minutes. You quickly note it. Then I will be proceeding further. Is it done? Noted? Okay, good. So now here are the K maps. You try to see. So these are all going to be four input K maps, that rather 4 variable K maps. This is going to give you the values for A. When A should be on, now we need to check all the combinations here. Under which conditions A should be on. So now you can check when A will be on. So now you can see when all A 0, B 0, C 0, D 0, all are 0, A should be 1. So that's what is written here for A, right? Similarly, you can check when it is all 0, 0, 0, D is 1, then it is 0. So 0 is written here accordingly. Then next is 0, 0, 1, 0. This is 1. When A0, B0, C1, D0. 0, 0, 0, 1, 0. This one. So there is a 1 here, right? And 0, 0, 1, 1. Then you can check 0, 0, 1, 1. There is a 1 there. 0, 0, 1, 1. There is a 1 here, right? I hope you can follow my words. Then there is 0, 1, 0, 0. There is a 0 at that place. 0, 0, sorry, 0, 1, 0, 0. Right? 0, 1, 0, 0. There will be 0 for that. 0, 1, 0, 0. This is the 0 here sitting. Then 0, 1, 0, 1. You come here. 0, 1, 0, 1. That's the 1 sitting here. Okay. This is 0, 1, 0, 1. This 1 sitting here. Okay. 0, 1, 1, 0. There should be a 0 for that. 0, 1, 1, 0. There is a 0 sitting here. Okay. Then you come further. 0, 1, 1. I mean 0, 1, 1, 1. So 0, 1, 1, 1. There is a 1 here. Okay. And then 1, 0, 0. Then you can come here. 1, 0, 0 means 1, 0, 0, 0. There is a 1 corresponding to that. I hope you can follow from here, right? Then 1, 0, 0, 1. 1, 0, 0, 1. So you can see here 1, 0, 0, 1. There is a 1 here. Now you will be seeing some X here. What is the meaning of X? Is don't care condition, because we are not using the combination of binary numbers beyond this, isn't it? We are only representing, because with the help of a 4-bit input system we can get 16 decimal numbers, isn't it? 0 to 15, but we are only using up to 9. That is, we are only using 10 decimal numbers. Therefore, all other bits are don't care. These are called don't care conditions. I mean, whatever they are, there is no concern of output with that. X. And these don't cares are really helpful in simplifying K-maps, in a sense that when you are solving it for sum of products, we will consider all those don't cares or X's as ones. What will you do? You will consider all of them to be 1. If you are solving product of sum, then you will consider all of them to be 0. Their don't care means there is no problem. I mean, you can take them anything. Output has nothing to do with those input options, right? So, okay, to simplify K-maps, we say, okay, let us take all of them 1. That will help us simplifying the K-map, right? Because if we have all of them 1, we will be in a position to get more quads, more octets, and so on. Similarly, what you actually have to do, let us not, I'm not, doing it right now in detail, but all other K-maps, so this is K-map for A, similarly this is K-map for B, K-map for C, K-map for D is here, K-map for E is here, F, G is here. So there are going to be total 7 K-maps, because there are 7 outputs, 7 LEDs. That is why 7 segment display, right? So now if you simplify this K-map, okay, let us try this. I leave it to you. I mean, just right now, you quickly solve this K-map, and then let me know what will be the Boolean expression corresponding to this K-map. Let us simplify, and then that will be the output option. Yes, try it. Look for all those quads. Now all these x's are nothing but 1. So assume all those x's as 1. Solve this K-map and then find out the expression. Yes, waiting for your response. Anyone, when you are able to get the solution, quickly type your solution here in the chat box. A or CD or BD or B complement CD. Others, yes, waiting for your response as well. I'll be showing up the solution then. You have to check if you are in a position to simplify or you have practiced things properly or not. This is a good practice indeed. Tanvi says A or CD or BD or B bar, D bar. Okay. Others, yes, yes. More solutions, please. A, C, D. Most of you are getting what Tanvi has got. No, Tanvi has got something different. All of you are getting a different solutions. So that's what you are going to get. Probably Tanvi has done it correct way. Is it A or CD or BD or what is Tanvi's solution? Tanvi was, I think, first to hit the right solution. A or CD or BD or B bar D bar. Yeah. So Tanvi got it correct. I don't know how many of you got it correctly. So you can discuss with Tanvi or even try it yourself again properly. Then that is for the solution which you should get. Um, Anyhow, if anyone of you has a doubt or question, for example, Abhi Kashyap could not get it properly, even Divyanshi did not get it properly. I don't know how many others could not get it correctly, but yes, if you have any question how we simplified this K-map, you can still ask so that I can help you understand this or I can explain. Or if you will get it yourself, that's great. But I mean, I'm here to help you out. Please ask your question so that I can help you. Yeah, any question? Abhi, Divyanshi, or Diksha says she got it. I think it is correct. Abhi or Divyanshi are two, I think, for which I can see that they didn't get it correct. Any question from you guys? I mean, you have any doubt, confusion? Why did you miss it? We have taken quads differently. So now that is the mistake. Now, at least you should, I think, be in a position to notice your mistake and then accordingly fix it up. Did you get the reason why you were wrong? You understood it, that what mistake you had done? Okay, Abhi got it, sir. I got it now. Very good. Fine. Now, let us try with the next K-map. Now K-map is sitting on your screen. You try this K-map for B. Let us see how many of you get it properly. You solve K-map for B, and then let me know how many of you get it correct. Let us see what you get. Yeah, go ahead for B. Very good. Okay, Sonali got it fastest. Very good, Sonali. I hope it is not wrong. It is correct. That will be nice. Anshika got it. Almost same expression. I would expect you to be honest. Huh? You just type whatever you are getting, and don't just copy paste others' work. Okay. And if you don't get something, you just feel free to ask. I will explain. Let us see. So that's what you are going to get for B. B will be B complement or C complement and D complement CD. I think most of you got it correct. Very, very nice. Very good. Rather happy for this. Okay, let us practice few more, right? Should we practice few more? Next one as well? Well, try this for C1. Now try for C. Try this K-map for C. What will that give you? Okay, very good. Some of you got it. Okay, most of you are getting the same solution. Very good. Let's see what it is. I don't know. Yeah, B or C complement or D, B or C complement or D. And how they have also written this one. So there we have used De Morgan's theorems. I hope you know what are De Morgan's theorems. Oh, Shubh, you are getting, I hope you missed C. I mean, or. This is a typo, I think. That's okay. It should not be CD, I think. C bar D. Huh? It should be C bar or D. Okay, fine. One more practice. You try for D. Try for D. I mean, this one. Try for this K map. Let us see if you get it correct. Yes. Yes, you got it. Very good. Divyanshi now is getting B complement D. Okay, you check your solutions. This is what you should get for D. I think most of you have understood the logic now correctly. That's very good. I mean, that's how you should solve. If you want, you can quickly try to solve for other three as well. It's just a practice. And once you understand that well, then you can solve for any truth table, any K-map. Let's do a quick practice of E as well. What is E equal to? Oh, what is N? Aditi, what you have written? B complement D N. What is N? Maybe it is a typo. That's okay. But still, I have. Aditi has done something wrong or what? I don't know. Maybe. Uh, okay. I have done for G. E very good. E is equal to E is very simple. B complement D complement C D. Okay. So very good. Similarly, F will come out to be equal to this one. F. If anyone got F, check if you are able to get this. Is anyone able to get F? F equal to this one, what I have shown on the screen. And then G will come out to be this. Okay, quickly try this and see if you can get these two. Now the solution came before you tried it, so that you can quickly look if you are able to get these expressions or not. So I'm sure now that you all can do this K-map simplification, and the main interesting thing is that once you know these expressions, then you will be having four inputs with you. How to design circuit? You will be having four inputs with you. Then somewhere you may have to put NOT gates, then some AND gates and OR gates, and then with the help of those basic gates, you can design your desired IC, which will actually convert the inputs from BCD, that is binary coded decimal form, to 7-segment display. So your circuit will have 7 outputs, that is A, B, C, D, E, F, G, and it will have 4 inputs, A, B, C, D. That's it. So you have to feed in corresponding decimal number, corresponding binary form of the decimal number, and then that will be displayed in the 7-segment display. So these kind of circuits are very important and very much applied in day-to-day life even today. So that's what is a very interesting aspect of these K-maps and simplifying circuits or designing circuits with the help of K-maps. Now, next thing which we want to discuss is data processing circuits. So basically, we shall be, now that's our next unit actually. So basically in this next unit, we shall be studying multiplexers. So what are multiplexers? So these are now the circuits which are used for processing data. Then we will be talking about demultiplexers. What is the role of demultiplexer as well? Then we will talk about decoder and encoder. So this BCD to 7-segment display is a sort of decoder, isn't it? Because your input is in the binary form and it is decoding that binary input to decimal form. So that's a sort of decoder. You can say, understand decoder like this. And then you can have opposite of it. Means you can have a keyboard which is having numbers from 0 to 9. And then when you press, say, 8, then you should get corresponding binary number at the output. So that kind of thing can also be done. Those are called encoders. So we will be minute. So multiplexer, what is multiplexer? First, let us understand what are multiplexers. So a multiplexer is actually nothing but n to 1 bit. I mean, you have n inputs, and what a multiplexer do, it selects any one of those n inputs depending upon what select input is given here. Right? Okay, so this is a block diagram for a 4:1 multiplexer. First, let me explain the operation of this multiplexer. So how this multiplexer work is, on the basis of this truth table we can understand. So basically what does this do? These are select inputs. So if I put, say, suppose select inputs 0, 0, then what will be y? All inputs are simultaneously available here. Okay. But what will be available at output y will actually depend upon what is the select input. So if the select input combination is 0, 0, this input will be transmitted to y, or this input will be transferred to y. So y will be equal to I naught. If you choose select input to be 0, 1, then I1 will be fed to y. Similarly, if you take this 1, 0, I2 will be fed to y. And if you take I3, if you have to take I3, then you have to apply 1, 1 at the select input. And that's how we can get any one of these inputs at output by playing with these select input options. That's the idea of a multiplexer. So multiplexer actually enables us to select any one of the inputs available at the input circuits. Then any one of them is selected at output based upon what address bit. So these can also be called address bits, right? Or select inputs. They are just giving you the sort of address to these locations. And these multiplexers are very helpful in using reading from memories. So by selecting this, suppose you have some data stored in these 4 locations. So if I have to read, suppose, data from this one, so what I will be doing, I will be giving the address. So this is like address bit for that memory location. So we will accordingly be applying the address, say 0, 1, and then data will be available to you from this memory location. So multiplexers are one way used for accessing memory. They are also used in designing simplified circuits also. I mean, just like we were using basic AND gates, or this mean OR and NOT gates, or NAND gates, or NOR logic to implement various circuits. Similarly, we can use multiplexers to implement any truth table. We will be doing that in coming lectures as an example. Is this idea of multiplexers clear, or any question from this? Is this idea clear? What is a multiplexer and what does it do? Okay. So now let's try to see what is the Boolean expression for multiplexer. What should be the Boolean expression? So this may be one way of looking at this. This is just, we didn't solve K-map, but you can try that also. We have just seen quickly, I mean, just a sort of hit and trial thing, that okay, this is what is going to look like the Boolean expression for this case, this multiplexer. 4:1 bit multiplex. This is called 4:1 multiplexer. 4:1 means you have 4 inputs, 1 output. Okay. So now you can understand very well here. I mean, when S0 and S1 are both 0, then what will be available at output? So this is 1, this is 1, right? Means S0 is 0, S1 is 0. So S0 bar is 1, S1 bar is 1. So 1 and 1, this will be 1. So whatever is I0 will be available at Y. So Y will be equal to this first term in that case. So these are acting like a selector bits, and this is like the input bit which goes to the output. Okay, so that's a simple way of looking at this Boolean expression of a 4:1 multiplexer. If you want to look for a circuit, this is actually the circuit for a 4:1 multiplexer implemented using NAND logic. That's one thing. I mean, you can even try it using AND OR logic. So this is a 4:1 multiplexer using NAND logic. How to understand the operation? Now you can see, let us try to see the output, I mean circuit as such. Say if both of them are 0, this is 0, this is 0. So what will happen? You notice this circuit carefully. There are two gates to which the select bits are going directly. I mean, this gate and this gate, they are getting the select bits directly. 0, and this is also getting 0 directly. Okay? And remaining two gates are getting not of the select inputs. So there is a not gate, it is going here, S1 not, and this one is going here. This one, yeah, going here, S1, S not complement, right? So two of the gates are connected directly to the select inputs, remaining two are connected to the complement of the select input. Okay, now how this circuit operates, let us see. So when both S1 and S0 are 0, so when both of them are 0, these two NAND gates are switched off, 0, isn't it? I mean, AND gate, AND component of them is 0. So what will be their output? Definitely 1, because this is a NAND gate. So whenever input is 0 to any AND gate, output will be 0. But this is an AND gate, so output will be 1. So these two will give you 1, correct? And what about these two? So these two will give you what? This is 0, this is 0, correct? So output, their complements will be 1, 1. So this is giving you 1. Here is 1 connected, 1 is connected. In this gate also, address bit gives you 1. Okay? So this gives you 1, this gives you 1. Fine. And what will be, okay, notice one more thing. There are three inputs here. There are three inputs here. So other is coming from here. Means to each of the AND gate, both select bits are going. I mean S0 and S1. Third is this input bit. So when these two are 0, this goes to 0, this goes to 0, as I already told, right? So this will be 1, 1. And along with this, what you are getting to this gate, this is 0, this one is 0. So this gate is both 0 inputs. Both 0 inputs means output is of course 0, whether it is one input 0 to a AND gate or two inputs 0 to a AND gate, output will be always 0. So for an AND gate, it will be 1. Here, what you are getting, here you are getting S1 directly. So this is 0. So this will also give you 1. Although it is giving a not here, right? S not is coming here. I hope I didn't confuse you with the connections. Okay, let me again repeat fresh. So what is it? In this gate, two inputs are coming from select bit. S0 goes directly and S1 also goes directly. Fine. Here to this gate, you will notice that S0 complement goes here, S0 inverted goes here, whereas S1 goes directly to this gate. To this gate, you will notice that S0 goes directly, you can see S0 goes directly here, and S1's complement goes here, right? Similarly to this last gate, both S0 and S1's complement goes. So now based upon this, you can realize that whenever these two are 0, 3 of the NAND gates will be giving you 1, 1, 1, right? So now what will be the output decided by? That will be decided by fourth gate, because for sure these fixes the output of these 3 gates. But then this one will be giving you what this gate will give you will depend upon what is the data bit here. Because to this gate, this is 1, this is also 1, right? So what will this give you? Whatever is I0 accordingly will be the output. So this will implement the first term. Similarly, you can try various combinations and then try to see what will look at Y. One more simplified way of looking at 4 to 1 bit multiplexer is this. This circuit is simplest one, okay, which actually implements not this 4 is to 1 multiplexer using AND gate and OR gate. Okay, so you can see here, Subhash, are you present? Subhash, are you present? So when I ask for attendance, then better to apply, better to type for your roll number here. Huh? Or you are just waiting that, okay, when you will type your attendance, that's all. Others are also there in the conference and they will also have to mark their attendance. And I know it well that you have to type your attendance. So I will ask you for that. Okay, everyone, you can type your attendance, fine, no problem. So now this circuit, you can see that, okay, you can see that this gate connects to B complement, isn't it? This gate connects to B complement, and you can see A complement as well. Okay, so this gate connects to B complement, A complement, so that whenever A, B both are 0, B complement, A complement will be 1. So this AND gate will be having 2 inputs perfectly or surely 1, right? So whatever is the output will be nothing but depending upon what is D naught. And there is a OR gate sitting here, so you can understand that, okay, when both A and B are 0, whatever is D naught will be transferred to the output. Whenever A is 0, B is 1, then you can check D1 will be transferred to the output, and so on. So that's also another way of looking at a 4 is to 1 bit multiplexer. 4 to 1 multiplexer. I hope this operation of multiplexer is clear to you. If there is any confusion, you can ask. Is there any question for this simple circuit of 4 to 1 bit multiplexer, or everything clear? Is everything fine? 4 to 1 bit multiplexer, or any question on this? Okay, fine. So in general, you can have a n to 1 multiplexer, for which you may have some select inputs depending upon, okay, what is the multiplexer size, and then based upon what are the select inputs, you can select any one of the inputs. So that's what is the basic idea of a multiplexer. So here you should notice this G bit. This is additional. So this is like, okay, input option which is used to enable the IC. It's like this circuit will activate this bit will activate the IC. This is a very helpful bit. We will see it in the coming classes. that this one, this bit will help a lot in selecting which multiplexer to read from. We'll be coming to this in the next classes, but okay. What is the role of G is like this. I mean, G complement and everything else like this. So the Y will be equal to this expression, any one of the inputs, only when G is 0. Isn't it? Only when G is 0, Y will be any one of the inputs depending upon what is the select bit. If G is 1, whatever is your select inputs, whatever is your whatever are your these inputs, nothing will be at Y. Y will be 0 always, right? So that means that the circuit is disabled. You can say this multiplexer is disabled or deactivated. So this is called activation bit, or you can say enable bit. So this particular case, in this particular case, this particular multiplexer is active low. Active low means whenever G is low or G is 0, then this multiplexer will be activated or active for the operation. In case G is high, this multiplexer will be deactivated. So that's active low and n to 1 bit multiplexer. This is how we can understand the operation of enable input or G for a 4-bit system. So this is 4-bit 4:1 multiplexer. So that's going to be the expression. This is a simple truth table. So that's all for today. Tomorrow we will continue with small discussion on multiplexers. Here is something like a 16:1 multiplexer. You can take a screenshot of this and then try to understand what is it representing. This is 16:1 bit, 16:1 multiplexer. Then we will move to further next things, that is demultiplexer and encoder and decoder. That's all for today. Any question you can ask so that I can answer your query. Is there any question from what we discussed today?